In this video, I'm going to go through how to name ionic compounds. Now, before you can name a ionic compound, you have to correctly identify when you have a ionic compound. So that's going to be when you most typically have a metal and a non-metal. Now, the ionic compound will be made by a transfer of valence electrons from the non-metal to the metal. Now, these valence electrons are the outermost electrons. That'd be the outer ring in the Bohr model. Now, it's always true that an ionic compound will have a positive ion, and we typically write that first, and that's the cation. It's almost always from the metal, but that's not a rule. You'll see some more exceptions in Chemistry 20. The negative ion that is written second is referred to as an anion and is pretty much always from a nonmetal. Now, the positive piece from the metal and the negative piece from the nonmetal will have to balance each other out. They form a very strong ionic interaction, and we need to be able to write a correct formula unit for the positive and negative pieces. Diving a little bit deeper, I'm going to use electron dot diagrams to illustrate why it's not always a one-to-one ratio. You're not going to have to do these electron dot diagrams all the time. You just need to use the charges, but making sure you have a good understanding before we continue. So if we look at a reaction of calcium atoms with fluorine atoms, so two neutral atoms, we can get the electron count or the valence electron count for our dot diagrams from the periodic table. Everything in group 1 has 1 valence, group 2, 2 valence. We're skipping the transition metals in the dot diagram notation to group 3A, which is 4, 5, 6, 7, and finally 8 valence electrons with our noble gases. So a calcium atom has 2 valence electrons, 2 outermost electrons, so 2 dots in an electron dot diagram. A fluorine is in group 7. So it's going to have 7 valence electrons, which we can model as dots. Now, what happens in the formation of this ionic compound is fluorine can become stable by becoming fluoride and gaining one of calcium's valence electrons. And then we get a fluoride ion. So in the electron dot notation, you put square brackets around your ions. Fluoride has 7, and it's a 1 minus. But we don't quite have a calcium 2 plus ion yet. We have an extra electron. So this reaction doesn't work in a one-to-one fashion. We need another fluorine atom. So this fluorine atom is also going to have 7 valence electrons, and that extra electron from calcium, the second one, can be picked up by our second fluorine atom. That gives us our calcium 2 plus. Now calcium has no electrons left, so no dots. So we get 1 calcium, but we don't have 1 fluoride, we have 2. So we're not going to draw it again, we're just going to put a subscript 2. Now this isn't nice and convenient to draw all the time, so what we want to be able to do is write a correct formula unit. So the formula unit for calcium fluoride is we write Ca, and there's 1 of those, we don't write 1s, and we've got 2 fluorides. And this is nice and balanced. The total charge of this whole thing is 0, and we don't write the 0. We also don't have to write that it's made up of a 2 plus and a 1 minus ion, but you need to realize it, and I encourage Science 10 students to actually write these charges out as you're working along. So let's practice balancing some formula units. So I'm going to do a few examples, then I'll encourage you to pause the video, and then I'll put the answers up one at a time for the remaining after the first 4. So we've got Ca and O. You have to realize the charges. Again, I encourage students to write them in, though you can do this in your head. We have calcium, which is a 2 plus. We have an oxygen, which is a 2 minus. You don't have to memorize these. You just need to have your periodic table for Science 10. Plus 2 minus 2, we don't need any subscripts. There's one of each of these, so we're done. We just have to realize it's a 1-to-1 ratio. Now in sodium oxide, we now have moved to a group 1 metal, which is plus 1. So this is not going to work without any subscripts. Plus 1, minus 2. So we need to balance these charges by finding the lowest common multiple and scale both up to that charge. So our multiples of 1 would be 1, 2, 3, 4, 5. Oxygen is going to be multiples of 2, 4, 6, 8. So the lowest common multiple is going to be 2. We have minus 2 already, and we need plus 2. So we don't need 1 sodium, we need 2 sodiums to balance the charge. So now that black is the correct answer. Moving on to beryllium, which is a plus 2 ion. It's not on its own going to balance a halogen or halogen ion, 1 minus. So this is another lowest common multiple of 2. We have plus 2, and to have minus 2, we need 2 of these. So this has nothing to do with fluorine coming in pairs that you might learn on the molecular side of this Science 10 course. So it's just purely balancing the charges. Moving on to Al and N, aluminum, sometimes a little tricky to find. It's in group 3A. Aluminum is 3 plus, nitrogen is 3 minus. So that's good, that's balanced. We don't need any subscripts. So now I encourage you to pause the video, and in about 5 or 6 seconds, I'll start solving these. So hopefully you want to see the answers now. If not, hit pause again and continue practicing. So we've got that plus 3 and then a minus 1 with chlorine in group 7. So we're going to need 3 of the chlorines to have plus 3 and minus 3. Cesium is in group 1. Oxygen is in group 6A, minus 2. So plus 1, minus 2, we need 2 cesiums to have plus 2 and minus 2. Now I'm going to write the charges in for the next one. Mg is a plus 2. And nitrogen is a 3 minus in group 5A. So you can't just put one number in to solve this. The lowest common multiple is going to be 6. We've got 2, 4, 6, 8, and 3, 6, 9, 12. So they overlap at 6. So we need to scale both of these up to plus 6 and minus 6. So Mg, we need 3 of them to have plus 6, and nitrogen, they're minus 3 each, so we need 2 of them to have minus 6. Now this is a correct formula unit. Again, the black is the correct answer. Letter H, we've got a minus 3 ion and a plus 1, so we need 3 of the sodiums. Lithium is plus 1, and iodide is minus 1, so that doesn't need any numbers. Potassium plus 1, minus 3, 3 of those. A plus 2 and a minus 2, so no subscripts. Calcium is a plus 2, chloride's a minus 1, so you needed 2 of those. And rubidium is a group 1, so plus 1, and a minus 1 in bromide, so that's balanced. So that's correct formula units, and identifying something is ionic. Then we can start moving through the rules. It's important with ionic compounds that you do not use prefixes. They're not used with ions. So naming ionic compounds when they're binary, so just 2 different types of elements, is fairly straightforward. The positive part, the first part, you leave unaltered, and I've typed those in already. The second part of the name, you're going to drop typically 3 letters, or drop until you get a consonant and then put in an "ide" ending. So for NaCl, the metal is sodium. The non-metal is chlorine. So I'm going to have to take away 3 letters, or until I get to a consonant, and in this case 3 letters gets us to an R. And then we're going to add in the IDE. So that's sodium chloride, a name you're pretty used to. Next we have calcium and oxygen. Now oxygen, we're going to drop 4 letters. If you drop 3, you get to a Y, which is a vowel sound. So we're not just going to drop 3. If we added I, it would have back-to-back I sounds. So take out one more letter, and oxide. With aluminum and nitrogen, you're going to have the same type of dropping a fourth letter. So OGEN in nitrogen. So if we take away 3 letters, you're left with a vowel. So we're going to drop that fourth letter. So this is going to become nitride. Last, we get magnesium and chlorine again, or chloride in the ionic form. So we've already done that. What I want to emphasize in this example is resist the urge to want to put in dye. We do not put counts in ionic compounds. You would figure out the count by looking up the charges, balancing the charges, and deducing the two. You are not told. So that's binary ionic compounds. Time to practice. So here's a whole bunch of practice. The formula units are already done. These are the same ones that we've done already. So you don't have to write them again, but see if you can fit in the names next to them. And hit pause in the video, and in about 3 to 5 seconds, the answers will pop up on the screen. So these are the answers for all those questions. I'll just highlight a few. Most of these are pretty straightforward from our notes. We've seen oxygen and halogens. We saw nitrogen turning into nitride. One is sulfur that we haven't looked at so far, and you just drop the UR in sulfur to become sulfide. Phosphide also pretty much follows the rules, but there's an extra letter dropped. So those are binary ionic compounds. Moving on, we're going to deal with the multivalent elements. So multivalent means that there are multiple possible charges. So we can't just name them like we've been naming, because the reader would know which charge it is. So where you find these multivalents is in the transition block, or with the transition metals. Now I've highlighted those in red. Most of the time you're just going to see the yellow ones, but you certainly could see some of the lower ones. You're going to add one little bit into the name for the multivalents. So if we look at iron, it's got the most common charge as +3, but then it has a less common but another charge of +2. We have to tell the reader which one this is. But if you look at zinc, there's no need of adding extra information because only +2 is possible. So most, but not all, of these transition metals require adding a Roman numeral. So if you have a 1 charge, you're going to see a 1 added in, a 2 charge. You're going to use a 2 for Roman numerals. If you have a +3 charge, you'll use the 3. If you have 4, which the Romans did as 1 before 5, so you have a 1 and then a 5 is a V. So 1 before 5. I don't think you'll need this high very often. We've got 5 next, 6 is 1 after 5, and then you have 2 after 5 and 3 after 5 for 8. 10 is symbolized with an X, but again, you rarely need to go that high. 1, 2, 3, 4, 5, and maybe 6 are the most common ones you'll see. So let's look at a couple examples. So we're going to add that Roman numeral right after the metal. Now I've already typed out the names for these ionic compounds, the metal as is and the non-metal switching to I, nothing new here. But now we need to tell the reader what charge this iron is. We can't go back to our table and put in the first charge because it may or may not be the most common. We're going to have to work back from the charge of the non-metal first. So our non-metal, our chloride would be 1 minus. So between the two of them, we have 2 minus. This formula unit has to be balanced, so this iron must be 2 plus to balance the 2 chlorides. So this is iron 2 chloride. In letter B, we've got Fe and N. Nitride is going to always be 3 minus. So we need this iron to be 3 plus to balance it out. So this is iron 3 versus the iron 2 in A. I would encourage you to pause the video, see if you can do the remaining 4, and I will be back going through the answers in about 5 seconds. So hopefully you had a chance to do them all. We've got cobalt oxide. Oxygen is always 2 minus. So to balance it out, we need a 2 plus on the cobalt. Fairly straightforward. F is the only one that's really going to have a little bit more of a complication. Chloride is 1 minus, but there's 3 of them, so that's 3 minus. So our cobalt has to balance that out. So it is 3 plus. So we use a Roman numeral 3. I'm not bothering to put the vertical lines. It just slows me down, but you would often see that. Copper and bromide. Bromide is minus 1, so there's 2 of them, so that's minus 2 in total. 1 copper, so that has to be plus 2. Now we've got more subscripts, a little bit more work to do, but the same process. Nitrogen is 3 minus. There's 2 of them, so in total there's 6 minus. So that means the coppers have to be 6 plus. But there isn't one of them like we've seen all along. There's 3 of them. This 6 plus has to be shared amongst the 3. So 6 plus divided by 3 of them would be 2 plus each. So make sure you don't put the total charge of all the coppers. It is just one of them, and each individual copper is A plus 2. So that's the multivalence. We've handled the binaries. We've handled the multivalence. Last in the ionic naming is dealing with polyatomics. So now we have more than 2 elements. So there are many ions that are made out of combinations of atoms. Now you will learn how to draw these in Chemistry 20. For right now, you just have to connect the count and the charge by name. So let's take a look at carbonate. Your Science 10 data sheet should have most of the common polyatomic ions. So carbonate has 1 carbon and 3 O's. And this whole thing is 2 minus. Now you might think, okay, the 2 minus applies to the oxygen, but that's not correct. It is this whole entity that is 2 minus. Again, you don't have a good understanding of these, or really any understanding. In Chemistry 20, you'll learn how to draw these, and this carbon and 3 O's have 2 extra electrons when you draw it, hence the minus 2 charge. So when you name with these multi-atom ions, you just leave the name unaltered. You don't change anything. So let's do a few practice. This just really requires looking up and correctly breaking up our ionic compound into 2 pieces. So your default is metal and non-metal is what you see 99% of the time. So sodium is our metal, so we're going to split everything else. So everything else is a CO3, that carbonate that we just saw. So CO3, now 2 minus makes sense with 2 sodium atoms being 1 plus each. So we just write the name. Do not change the ending to "ide." Next one, we get Li and NO3. So we've got a metal. So in our head, you don't have to draw a line, but we're splitting that in 2 pieces. Lithium, you name the metal unaltered, and we're going to have to name the polyatomic ion unaltered. So NO3 is right here. Ooh, sorry, one above it, almost, is nitrate. Now the convention for these names is the higher oxygen count atom is the 8 and the lower is the ite. So you see this here. Nitrate has more O's than the NO2, so we call this the 8 version, and we call that the ite version. And there's a modification of the 8 and ite when there are more than 2 options. So see if you can do these last 2, and I'll put the answers up very soon. So hopefully you paused the video so you could name those last 2. So we've got Ca, so we're going to split it. There's our metal, and then we've got everything else. Now we've got some brackets. The brackets and a number just means we have 2 of something, so we have 2 of these PO4s. So we've got to look for PO4. Don't look for PO4 and then a 2. So PO4 is phosphate. Now 2 phosphates were needed to get the formula unit to balance. Now we do not include counts. We don't go diphosphate. We just, with ionic compounds, use words. So it seems a lot more complicated with the brackets and the doubling, but it's not. The last one, we've got NO2. There's 2 of them, but we don't put di. NO2 is nitrate. And then I was testing to see if students could still remember the previous rules. Iron is multivalent, so we have to put in a Roman numeral. We're going to have to figure out what the charge of the iron is. Now nitrite is minus, or 1 minus. There's 2 of them, so that's -2. So we must have a 2 plus iron. So this is iron 2 nitrate. So that concludes naming ionic compounds. Next in the video series, we'll be naming molecular compounds, and this is where the prefixes mono, di, tri come in.